Hello, welcome back to the year 2020. Starting off the year, Scholar Style doing Algebra 2. Exponential models. These formulas are kind of really important because they have some context to them. Usually we just find x and we don't really know what it is. So we do word problems, but they don't really apply most of the time. We just make up problems to fit. But here, we're doing some exponential growth, and it's represented by this formula here. But basically, it's when a real-life quantity increases by a fixed percent each year. It's modeled by that equation, where A is your original or initial amount, R is your growth rate, and that's in percentage. T is time, and 1 plus R is our growth factor. Okay, so let's do some examples. So number 1, in 1970, the population of Kern County, California, where Bakersfield is located, was about 330,000 people. I should fix that for a sentence. From 1970 to 2000, the country population grew at an average annual rate about 2.4%. Try an exponential growth model giving the population Y of Kern County T years after 1970, approximately. Okay, so write an exponential growth model. So we're just following that formula up there. Y equals our initial amount, which is 330,000 people, times our growth rate, which is 1 plus R, 1 plus 2.4%. So remember, we don't use percentage in our calculation. We make it into decimal by moving 2 decimal places to the left. So this is 0.24 or 0.024. So let me erase that. And then to the t power. That's our equation. Okay. So they want to estimate, or they want to guess how many people lived in Kern County in 1990. So from 1970 to 1990, that's 20 years, so T is 20. All right. Yep. So T is 20 years, so that's from 1970 to 1990. And then you just plug T into the equation. You get your calculator, plug it in. So you're going to do 330,000, or actually you do parentheses first, 1.024 to the 20th power, and then times that by 330,000. And there was actually about 530,290 people. I'm guessing this is part B, so this is part C. Graph the model using a graphing calculator, then estimate the year in which the population of Kern County was about 400,000 people. Let's go to my graphing calculator then. So we're graphing. We go to graph, or no, y equals, plug in our function here, 330,000, 1, 2, 3. Then that was to the times 1.024 to the 20 or t power. So we're going to use x in the graph. So when we try to graph it, we're getting nothing. So we need to change our window. Once it lets us. Still. So our x minimum represents our time. So we can't have negative time. So we're just going to put that at 0. And then let's have a maximum of 25 years. Our y value is in... We know it's our minimum is 330,000. So let's have, I don't know, a maximum of 600,000. So we're going to graph that. And look, there it is. So we go to trace, and then go to the 8th year. So I just typed in 8. Oh wait, what are we looking for? Oh, okay. So we were just estimating the year where it reaches about 400,000. So that's 8. So you would just test every year until you got as close as you can to 400,000. So I would type in 7, 8, you're typing 1 and then 2, then see how close it gets to 400,000. 9 is pretty close to 400,000, but 8 is closer. Okay. Let's move on to the next part. Alright, actually, number 2. Rabbits. Yeah, this is what exponential growth usually deals with, is population growth. Mostly that sort of thing. Rabbits usually come to mind. Scientists like to look at different creatures in their population growth. Oh yeah, rabbit population beginning with 25 rabbits doubles twice a year. How many rabbits will there be in 3 years? So using the formula, we start off with, so y equals 25. And then our 1 plus r, so 1 plus our growth rate is 100%. So, and then we're going it to the 3rd power. So y equals 25 times 2 to the 3rd power, which is equal to 25 times 8, which is... Oh, doubles twice a year. My bad. So it doubles twice a year. That means if it's 3 years, it's actually 6, the power of 6 here. And then, alright, so I was interrupted. Where were we? Doing bunny rabbits. So, once again, the t-value this time is 6 because it doubles twice a year. So after 3 years, the time at which it doubles hits 6 times. So 25 times 2 to the 6 is equal to, so y equals 1,600 rabbits. Damn rabbits. So after 3 years, 1,600 rabbits. That's crazy. Alright, next. Exponential decay is usually has to deal with depreciation depreciation is where you buy something and then it goes down in value over time as you keep it, which is usually like cars, vehicles. Okay, here we go. So, and it's presented by basically the same formula, but instead of 1 plus r, it's 1 minus r. My A value is still my initial amount. I don't know why it's in the middle. Rate is the decay rate this time, because this is the exponential decay model. Time is, or t is still time. And then this is the 1 minus r decay factor. So let's do some examples. New snow machine costs $4,200, so that's our initial amount. And it decreases by 10% each year, so our decay rate is 0.1 or 0.10. Right next to the decay model, giving the snow machine's value y dollars after 2 years. So y equals 4,200 times 1 minus 0.1 to the t power. Then estimate the value of the snow machine after 3 years. So y equals 4,200 times the quantity 0.9 to the third power. And we'll get so your snow machine is going to be $3,061.80. And this is just plugging in your calculator. So you went from 4,200 down to $3,061 in 3 years. It's not bad. Part B, graph it on a graphing calculator, then estimate when the value of the snow machine will be about 2,500. I'm going to skip the graphing part, but it's about 4.9 years. Number 2, a new car costs $32,000, so that's my initial amount. Car value decreases by 15% a year, so it's to be 0.15. So times 1 minus 0.15 to the t power, which is t. That's my decay model. And then t equals 4. If t equals 4, I plug it in the equation and I get 16,704.20. And then graph the model. Just use Desmos or your graphing calculator. All right.